an identity like x less than or equal to expectation of x? इस किस्म की है क्या identity?
KUFM.
And you? Okay, let's keep expectation for now. है ना expectation? ये ना क्या है? एड़ा रुकना जो भी.
Yes, I have expectation. MIT लिख रही है सर.
MIT की लिख रही है, किताब में भी होगा तब. किताब में भी होगा तब. चलें ठीक है जी. Okay, so what we did? So here's the thing that we are doing. So the first I would like to talk about the integrand of this. So the E to isometry is telling you that the expectation of this stochastic integral equation is equal to the expectation of this deterministic integral. And now I can play with this. So what would be the expectation of 0 to t b square of s x s and ds? So I can run same, what do you call, linear growth argument. So it's going to be the expectation of 0 to t c square and 1 plus, x of s square and ds. Okay? So you have the same actually. And by running the same argument, you can get a constant, for example, C3 plus C4 times the expectation of, times C3T, okay, the same argument, times T and X and ZT, what do you call, square? Are you getting the point? Okay? So once this becomes a deterministic integral, the argument is really the same argument as the previous argument. Okay? Just repeat the argument. So thanks to E to isometry it works. So what does this show? That all three terms are okay and phi is well defined. So step 2. So the step 2 it is to choose or make this t small enough, okay, to make this capital T small enough so that this phi becomes a contraction. Okay? Phi becomes what? Contraction. Contraction in ZT. So for phi to be a contraction, it needs to be at least Lipschitz actually. So let's see that whether it's Lipschitz locally or not. So let's say, for example, first compute phi of x minus phi of y and its square in ZT norm actually. Let's see what we get. Okay?
Yes, sir.
So when you're going to get, what would be the outcome? So phi of x, so initial condition is going to be same in both. So x naught will go away. Okay? And then their difference is going to be equal to what? Is going to be equal to 0 to t, okay, expectation of a here and a here. So phi of x is going to be what? X naught plus deterministic integral plus stochastic integral. Phi of y is x naught plus deterministic integral plus stochastic integral. So their difference, and so you're going to get this kind of an expression. What expression you're going to get? So 0 to t expectation of a of x s minus a of s y of s square and ds. ठीक है? नहीं, ठीक नहीं. So I'm gonna have, okay, write it precisely. So first of all, I need to do what? So I need to integrate this 0 to capital T of the expectation, okay, of the integral of this integrand actually. Okay, यही होगा ना, expectation of, okay, this phi of x minus phi of x of t minus phi of x y of t square and dt. Alright? And then substitute the value of phi of x and phi of t. When you're going to substitute the value of phi of x and phi of t, you're going to get 0 to t expectation of the integral from 0 to t of a of what? S x of s minus a of s y of s n square and what? ds. Right? So this would be the one term. Individual square और सबके ऊपर square. ठीक है? Plus 0 to t b of s x of s minus b of s y of s and dw of s and the square actually, right? And then you have finally a dt. ठीक है? So I just.
So is x not equal to y now?
I'm sorry? Yes. Not x not equal to y. X not is the initial condition for entire problem. So no matter what solution you have, no matter what phi x you have, x naught would not vary actually. Okay? X naught would not vary. So x naught is same for all processes. ठीक है? Is it making sense? So what do you think? What should be done next? Let's estimate this by. So it's all estimation actually. So you see, one of the things that you're going to observe, that proving inequalities and driving inequalities, how you can express the given thing in the terms of the basically things that you know. So it's really art of inequalities actually. Okay. So I want to use on this square, I want to use this actually, inequality. A square, a plus b square is less than or equal to 2 times of a square plus b square, okay? So by that inequality, I'm gonna say I can estimate this by integral 0 to capital T, okay, of expectation of 0 to t a of s xs minus a of s
Y of s.
ys, okay,
Yes.
and
It's integral.
it's a square and dt. Plus, I'm going to have a 2 here as well. Plus 2 times of 0 to s j.
सही है.
ठीक है?
Integral का.
0 to t but ds यहाँ
हाँ
होगा
सही.
ना.
ठीक है. सही.
ठीक है? It's going to be so.
Fine.
Keep track of brackets
ठीक है.
correctly. 0 to t and 0 to t b of s
और expectation.
x of s minus b of s y of s and ds
dws.
dws
Square.
and its square.
और expectation भी होगी. Expectation.
Yes, expectation भी होगी and
dt.
dt.
dt actually. ठीक है, you have it. Now, do you think what property we're gonna need now? Now we're gonna use the Lipschitzness of A and B actually. You remember? A and B are Lipschitz. So I can estimate in second component. So I can estimate this by
K1 times.
0 to t expectation of 0 to t of
K times x minus.
k times, so I can keep this k square outside. Okay, I can keep this k square outside.
X minus. XS
So
minus.
it's going to be x of s minus y of s and ds
Square.
is square actually. Right?
और dt.
ठीक है? स्क्वायर ओवरऑल होगा
सर जी इंटीग्रल
ओवरऑल
dt
ठीक है ऐसे ही है
हाँ सर dt
plus 2 times of
again
I'm gonna have k का square 0 to t j
k दोनों में सेम बात नहीं है केवल k
नहीं एक ही है k
अच्छा।
if you see the assumptions we have the same k for the both actually so you have this expectation of 0 to t and
x of s minus
x of s minus y of s
dw of s
dw of s
square
square and right
So don't you think इसका इंटीग्रल के अंदर आएगा?
नहीं think about it
so by integral
so
we
I'm
sum up
treating this as a and this as b
For
again
integral plus b square. For integral.
I'm sorry
For integral को आप a ले रहे हैं.
yeah so square है ही square के अंदर यही दो sums हैं so I'm treating this entire as a plus b square
the whole square less than equal to 2 times
ठीक है so you have a better choice I mean you have a book in front of you you can read it for yourself okay is it making sense alright so what should be the next thing now what is this guy what is this guy this entire guy can I say it's something this is the norm of x minus y zt norm actually
सही
okay so I can say that this is going to be really 2k square
0 to capital D
and you know t
हाँ सही
because this is going to be a number
सही
okay
times
times the norm of x minus y square in zt
सही
okay x minus y square in zt if I wish I can even क्या मतलब
नहीं अंदर रहता है सही बात है सर स्क्वायर इनके एब्सोल्यूट के ऊपर होना चाहिए था
मैं भी इसका की बात कर रहा था. ये अंदर होगा. एब्सोल्यूट पर होगा इसका.
अच्छा
ये सर.
वही बेटा वही
k times होगा ना वो.
एक तो बार इक्विवेलेंट टर्म
but we need to justify it actually अच्छा स्क्वायर इसके अंदर होगा 2a स्क्वायर बट स्क्वायर क्यों अंदर जाए ये भी तो देखें
नहीं नहीं इस स्टेप
so in other words you are saying let's put the square here actually
हाँ
okay
वही बीच में ले
so you're gonna get this
This.
ठीक है how about this one
2k square वही से
now so again e to isometry
लेकिन यहाँ पर सर हाँ ठीक है
e to isometry
वही
ठीक है so you can again apply e to isometry and you're gonna get 2k square t plus x minus y zt square actually ठीक है let's put a square on the t's actually it doesn't make any difference think about it कर सकते हैं
हाँ
चलो नहीं करते हैं
अगर ना दे
so we are we going to have okay shall we अच्छा पहली बात ये है कि in order to even estimate this by this or equating this by you need to have a capital T here यहाँ capital T होना चाहिए but you know since this integral you know non-negative integrand so you can estimate it by the capital T so you get this actually ठीक है चलो let's keep T as it is okay we have ठीक है so what did you get so the thing that we got is this that phi of x minus phi of y square you know if I get rid of a square is that the t can be estimated by 2 you know okay square root of 2k or maybe square root of 2t k
Norm
and
of x
2
times norm of
and norm of x minus norm of y square, square on the okay. Exactly. ठीक है? So you get this. So this shows that this is Lipschitz. ठीक है? But I want to make it a contraction actually. So I want to make this contraction. So in this constant, so I want to make this constant less than 1. In this constant, on what variable I have a control actually? So k is fixed for me. Okay, so k is fixed. I don't have a control over the k. The only thing that I can control
Now we'll
is really t actually.
make the, now we will use T1.
Yeah, so I'm saying that choose, okay, t small enough, and that small enough choice is, let's call it t1. Okay, let's call it t1.
such that this quantity
Such that this quantity, this 2 square root of 2tk is less than 1.
1.
Okay, such that this quantity is less than 1, and hence you will have that phi is a contraction. ठीक है? समझ आ रहा है कैसे चूज कर रहे हैं? So what you can do is this: directly take this and take less than 1. Okay, and then solve this inequality for t. Okay, and give that t a name actually t1. Getting the point? That's what is going to be. So what is the conclusion of this? The conclusion of this is
T1
the conclusion of this is that
phi is contraction of 0 to T1.
yes. So the phi is contraction. The phi is contraction. On yes. 0 to t. Okay. I'm not going into step 3. You see it for yourself. Okay. So I'm directly by Banach fixed point theorem. I can say that there exists an x. Okay. So by from directly going to the step 4 actually. Okay. So by fixed point theorem. So I hope everyone has heard of fixed point theorem. Okay. So there exists an x that is defined on the interval 0 to t1, okay, such that phi of x of t is equal to x of t on t belongs to, for all t belongs to between 0 to t1. So that's really a solution of what do you call SDE on, what do you call SDE. ठीक है? Would that be unique? So you're going to have uniqueness for sure, because fixed point theorem also gives you unique existence of such point actually. Okay, so I'm not really getting into the point 4 as well, because point 4 explicitly shows that the solution must be unique. Okay, so we can show it's unique actually. Okay. Why? Okay. So why are you gonna have this x to be unique actually? So imagine there is another, y, which solves or which becomes like phi of y equal to y. Okay. Now for those x and y, since phi is a contraction, should satisfy this inequality. Agree. So let's assume that y is another solution of it. Okay. Since phi is contraction, so it should satisfy this. But since x and y are the fixed points of it, so this would be, x would be equal to phi of x and y would be equal to phi of y, which is a contradiction now, because you have the same number appearing on.
Yes.
So you have the same number less than itself.
So y is equal and
I'm sorry?
y x is equal to
देखो ना भाई, हम ये कह रहे हैं कि this fixed point, in other words, the solution must be unique actually. Okay? So it must be unique. So phi of x is x and phi of y is y on 0 to t1. So they can't be two different things, because if they are different, you have a contradiction. So you have no choice except saying that x and y are same. So the uniqueness is really a simple thing. So even there is no point of proving uniqueness, because fixed point theorem gives you unique actually. Fixed point. Okay? So there is no point of proving uniqueness. So what is the next thing? The next thing is this step 5. How can I extend the solution? So see, I'm going through this detail. I'm taking this pain to go through. It's really. I mean, if you think there is nothing too much fancy in this proof actually, so a proof is readable. Just keep on reading it. You keep track of it. Everything is simple actually. So there is nothing too complicated in it actually, because the proof is readable. But I'm going through it for once. Because at least you should, if there are some gaps, you should see those gaps as well. So what is the step 5? So the step 5 is to extend the solution. Okay, extend the solution. So what we have done, so we have solved our, SDE star. So we have solved star on 0 to t1 subject to condition what?
X naught x. X of 0 x.
Subject to x of 0 being x naught. Okay? X of 0 being x naught. And this solution x is valid on this entire interval actually. And now I'm saying consider again is star, but subject to the condition
x1 condition.
x of t1 to be x1 for example. Okay? Okay? So what can I do? I can repeat the same argument, okay, and I can have another solution that is going to be valid on what? So this is valid on 0 to t1, the other would be valid on t1 to 2t1 really. So by same argument you have the solution, what do you call t1 to
2t1.
2t1 actually. Okay? Same argument. And I can keep on doing it actually. समझ आ रही है बात? I can keep on doing it, and then I can have a solution next, okay, that is really going to be okay. So what should I call this solution? Alright, solution assigned doesn't depend on the initial data. Contain coefficients of equation will be ठीक है. So what we can have, so by similar argument I'm going to have a condition, I'm going to have a solution on the entire 0 to t. ठीक है? So in other words, on each subinterval you have a solution, you put them together and give that a name again x, which is defined on in the entire interval 0 to t, and it solves what we call the SDE. Are you getting the point? Now, the problem that you can identify is that each of the solution on each subinterval has a different initial condition actually. Has a different initial condition. But we need a solution that has this initial condition x naught actually. But my argument is this. So you have this solution on 0 to t1. This solution, enforces you, enables you to construct another solution actually onto the interval, what do you call, t1 to 2t1 actually, and so on and so forth. So for all these solutions, the triggering point is really x naught actually. Okay, so when you are extending them, the real thing that is responsible for existence of all these solutions is again, what do you call, x naught and the contraction of green phi of x1. So there is nothing, what do you call, wrong in it actually. Is it making sense? Okay, so you can read it and further you can go there. So there are details here. So the last thing is to show the uniqueness of it. Sixth step is the unique. And the good, so you don't have to memorize all this. This is just for your understanding. Okay, you should see this, that why argument works. Okay, so don't worry about it, just enjoy the flow. So one argument is, so one way to solve, for example, such kind of SDEs is this, what do you call this, running a fixed point argument. And the other method, there are plenty of methods. The other method is, Galerkin approximations actually. It's a Galerkin method. So, you take your infinite dimensional problem, you turn it into the finite dimensional, you solve it in finite dimension and then pass the limits. Anyway, so there are plenty of methods as well. So how can I show now, what do you call, uniqueness? Okay. Will you see for yourself, proof for uniqueness from the book actually? It's straightforward. So it defines in a stop process and then, it talks in the terms of the stop process. Is straightforward actually argument. I mean, if you get any trouble, you can ask from me. So maybe you need a Grunwald inequality first, but the Grunwald inequality is inequality 5.4 actually, so you can see easily. Okay. So read it for yourself, not getting into the more details of it. Okay? But it's straightforward, like the way you have done it. What is the last thing that I would like to say? I'm not proving it. You can read it for yourself from the book. The proofs are readable. So for such kind of SDEs, what does be shown? XT, dWt, and x of 0 is x naught, where x naught satisfies this condition that expectation of x naught square is finite. Okay? So what does the previous theorem shows? That there exists a unique solution. Okay? There exists a unique solution. So let me write a theorem which even further tells you some interesting properties of such kind of a system. So the theorem is this. I'm not going to prove it, just going to throw this to you. And then I would like to move to some other stuff that I found today. Okay, so what is the next thing? This solution satisfies some uniform estimates actually. Okay? So in other words, it's going to be, always controllable actually. So it's not going to explode over the, what do you call, time. So here is a, and its solution is also, what do you call, a Markov chain. Okay? So for any solution, of x of a star, and why saying any solution? Because you can change the initial condition and get a different solution. For every solution is triggered by this initial condition. So for any solution of a star, and for any time t less than or equal to t, it satisfies this estimate. This is very useful estimate. So expectation of the supremum of x square of s, where s is in the interval 0 to t, is finite. Okay? So that's really a uniform estimate. Remember?